Welcome back to Multigrid Methods. Today we're going to recall the definition of the fast subspace descent method, and we're going to, with all hope, prove that this method is convergent using the same techniques that we employed to prove the convergence of the SSO method. It's probably good to remind you about the definition of the FASD method. So let's get into that first. So this is all a review, more or less, from what we talked about last time. And just want to recall to your memory the precise details of this definition. The idea is, of course, we want to solve some sort of optimization problem, but really underlying everything is the fact that we want to solve this PDE. So a certain PDE comes along, we realize it has some nice structure and it can be related as the Frechet derivative of a globally convex function, some functional, some energy, which is strongly convex and locally Lipschitz smooth. And if we can do that, then we can apply any of these algorithms that we've been talking about to solve this. So underlying this problem, we're always thinking that there's some nonlinear PDE that we really want to solve. So the FASD method is an algorithm. It's an iterative algorithm which produces, or recursive algorithm, which produces the next iterate from the last one. And it does so as follows. Recall, we take an initial guess. So that might be U superscript 0. That's the initial. But now once we have our kth step done, we're going to try to update to the k plus first. And the way that we do that is we first set V0k to be UK, and then we're going to cycle through these subspaces. So we've got a bunch of subspaces in our decomposition. Remember, underlying everything, of course, is the fact that we've got this decomposition of subspaces, which is stable and has other nice properties as well. On each one of these guys are going to live an energy. And so when we solve each of these subspace problems are going to involve solving these energy perturbation problems, which we're going to describe now. So we loop through these subspaces from 1 to n, and the first thing we do is we calculate something called the tau perturbation, which we'll try to explain later in some detail why it has the form it does. We're going to take the current iterate, this v iterates over the subspaces, and we're going to push that down through what's called a projection operator to the space vi. Okay, so that's where our energy EI lives, and this is what's called the full approximation. Okay, the full approximation, and this is what we're storing, and this is why it's called, or in the previously it was called full approximation storage method, but this is that full approximation again. We're going to calculate something called the tau perturbation on over the space I. So this is going to be an energy which is defined over VI. Okay, or not, sorry, not an energy. This is going to be a functional which is defined over VI. And so this functional is going to be a member of VI prime, the dual space of VI. And it's defined as follows. It's the Frechet derivative of EI. That's the energy over VI, whatever that is, we don't know yet, evaluated at the full approximation, minus restriction of, so this restriction operator we described last time is kind of really doesn't actually have to be here. It's just a kind of placeholder, really, of the derivative of our ambient space energy E. So this is the energy defined over all of the big space V. evaluated at vi minus 1k. So that's this object here is the current best iterate that we have, but on the fine grid space, not projected into these subspaces. So this guy still lives in V. This whole thing is the difference of two operators, difference of two linear operators on VI. And so they're bounded linear operators on VI. So that's their this difference is in VI prime. So that's called the tau perturbation. So we have to put that in our pocket for now, but we're going to come back to why that's useful to us in a moment. Well, probably 30 minutes from now. And now we take this and we're going to put it in a variational problem, and we're going to solve for this object called eta ik on the, and again, this one's going to be this, the solution of this problem is going to be on the subspace. So we're looking for eta ik in the subspace that satisfies this variational problem. You can think about this problem as just being a weak form problem as usual. Of course, in finite dimensions, we can convert this into like a nonlinear problem or a matrix problem, something like that, something in finite dimensions. Now, once we get, so there's the tau perturbation. This thing is bound up in this operator here. So this is in general some nonlinear operator because EI is not quadratic. We find out what this guy is, eta ik. This is like our coarse grid problem, right? So the idea here is that that should be cheaper than the problem on the fine grid. Once we know what this eta ik is, we're going to subtract from that the full approximation, psi ik, so eta ik minus psi ik. And now in the FAS method, we would be done. This would be our correction. Here, we're going to go one extra step. Instead of using this just as the correction, we're going to use that as a search direction, and we're going to find the correction along this direction. What I mean by that is we're going to consider an optimization problem for E, okay, along a direction. So this is like a one-dimensional problem. So this is, in fact, this whole thing here is like an energy section. You start at this point, but you're going to look along a certain direction. So the image of this, or the picture of this, is we're trying to get to the minimizer. And at the moment, we're like here with Vi minus 1k, and we're looking along a search direction Sik. And we're going to go along there until we reach the minimum of that energy section. And that's the same as solving a local Euler-Lagrange problem along that direction. The import or the upshot of that is we're going to get a value out of there called alpha ik. That's going to be the value along that one-dimensional space which minimizes this energy, okay, along that direction. So that's remember, it's an energy section, so it's a local parabola. So we're just going to go to the bottom of that parabola. Once we get that alpha ik, we're going to pair it to Sik, that search direction, and now that is going to be the correction for our scheme. So the big difference between this and the FAS method is the following. All we're going to do is instead of doing like instead of in the FAS method where we stop with the SI being the correction, we're going to do a process called orthogonalization. We're going to orthogonalize that S parameter, or that S value, and once we do that, then we get a correction out of that EIK alpha ik times SIK. So, or epsilon ik is equal to alpha ik SIK. That's going to be the correction. Now, what do you do with a correction? We always do the same thing with a correction. Once you figure it out for a subspace, you're going to add it on to this previous best guess. This guy, remember, lives in the parent space. This lives in the subspace, so you're adding a subspace object onto something from the ambient space. You could put, like we described last time, you could put an injection operator here. Injection simply means you're taking something which lives in the subspace and you're pushing it to the parent space. Really, there's nothing to do there because if it's truly a subspace that it already lives in the parent space. So oftentimes these added little operators are just to remind you that you're going from a subspace all the way back up to the parent space. All right, now once we cycle through our loop, remember our loop is going to end there. Once we've done this n times, then we end up with this correction vnk, and that's what we're going to call our updated value uk plus 1. All right, so the biggest difference between FAS and FASD turns out to be what I mentioned. Instead of stopping and making SIK our correction, we're going to orthogonalize that SIK and make that our correction. We're going to orthogonalize at that step. So that's the big difference between FAS and FASD, that one step. And that turns out to make the difference because we can now prove convergence when we use FASD, but we couldn't prove global convergence, for example, when we used FAS. It does require an extra step, and the extra step, of course, is that orthogonalization step, and that does come with a cost. We still have to minimize something. In fact, it's an energy section involving the original energy, which can be expensive. But the nice thing is it's only along one dimension. So it's not as costly as SSO where you're minimizing along a full subspace. Okay, so we're only minimizing along one dimension. And what this is called a line search. So you might have heard of this done so this is big in data science whenever you're doing the gradient descent method or the gradient, I guess it's called the gradient descent method. You're always doing what are called line search operations or line search algorithms. Okay, so line search is one of the biggest tools you have in your tool bag. But now again, we have a method which looks a lot like FAS, full approximation storage scheme, but it's not because it requires this extra little step of orthogonalization. But as I said, that makes the difference of being able to prove convergence or not. Now, here's another remark that is quite important. We don't have to go through all the details of it, but it's basically this. So FASD is exactly the same as SSO whenever we make certain choices for our local energies. So for example, if I fix a couple of values, for example, let me take E evaluated at this difference of points. So what is this difference? This point here this is the pre full approximation, and then here's my full approximation. That's the projection of the last best guess into the subspace, the difference of that. And I'm going to add on to that some value eta, where eta can be anything in VI. I'm going to define that as being my energy over VI, my local energy EI over VI. If I do this, then my FASD method gives me right back SSO. So that means that FASD is a generalization of SSO. It's just a particular choice of my local energies. Okay, if I make this particular choice of the local energies, then I get back to SSO. But that means that actually, remember, SSO is very, very simple to state. It's very subtle, very simple. It's not as practical to implement, but it's very simple to state. Remember, there was no tau perturbation term in the SSO. And it turns out if I make this choice, then the tau perturbation computes exactly to zero, precisely zero. And then my orthogonalization step is redundant. I don't have to do the orthogonalization step because when I solve with a tau perturbation being equal to zero, I'm basically solving an orthogonalization step to begin with. So this is nice because FASD generalizes SSO. And furthermore, we have already seen that it generalizes FAS. So it's a new method, entirely new, but it has these nice generalization properties. Now, the reason why we use the tau perturbation is going to be obvious, but only at the very end. And maybe even then not quite so obvious, but hopefully more obvious at least than now. All right, now the convergence strategy is exactly like we employed for the SSO method. What we try to do is we come up with a lower bound on corrections of this form, 4, and an upper bound on corrections of this form, 5. So the corrections that I'm referring to are these epsilon IKs, epsilon IK. So we need to try, so if we can establish a bound like 4 and a bound like 5, then we have a little technical lemma, which I call the golden key. You just turn the golden key and immediately you get the convergence of the method. No matter what the method looks like, if it involves something like this and with corrections, etc., then, and of course, FASD and SSO do, they're methods involving these corrections in these very simple ways, then I turn the golden key, I get the convergence of the method that I want. So the strategy is to find the CL and the CU. Now, it turns out the lower bound in corrections is very simple, and it's a lot like the proof that we employed for the SSO case. We just have to remind ourselves of a couple of key facts. Now, due to the line search that we do at the very end, remember I said that's the key difference between that and FAS method. Due to the orthogonalization that we do at the very end, we're going to have a nice property that we can employ to get this lower bound on corrections, as we'll see shortly. Now, since we do that line search at the very end, we have this equality. This is what's called the fundamental or Galerkin orthogonality, or the fundamental orthogonality property. This W comes from this space, okay, the span of SIK. Now, this is not VI. This is not the same as VI. VI is bigger than this. This is the search direction that we computed at the next to last step of the FAS method, or maybe the next to next last step. We computed a search direction, and then we did a line search along that direction. Well, if you look into it and investigate it, doing that line search along that direction means that we're going to have an inequality like this. And this is what's called the fundamental orthogonality. Fundamental orthogonality. All right, now let's put things together. So the difference between the old best guess and the new best guess as I'm going along subspace by subspace is epsilon I. It's the correction. But remember, the correction is just a constant. This is a real number times the search direction. So that's in that spanning space SI. So now let's do a very basic little calculation. If I do E of VI minus 1K minus E of VIK, then because I have the orthogonalization step here, I have the lower quadratic trap. Remember the quadratic trap? So along this direction, I have this quadratic trap that I can apply at this step. That says that this difference is bigger than that difference. So that's the quadratic trap part. And of course, this difference here is just my correction, okay? And the quadratic trap applies with the lower bound mu over 2. Okay, that's because we're using the original energy. Now we just use the fact that we can telescope these differences. I'm going to write E, remember E, so UK, that's equal to V0K, and UK plus 1, that's equal to what? VNK. And now I'm just going to write in between all of these numbers, I'm going to write differences which look like this, right? And so then I get this nice telescoping feature. And then each one of these differences is bounded below by that. So I'm going to insert that. So I get a sum of those differences. Of course, the mu over 2 comes out of the sum, and we immediately get the result that we wanted. So this is the lower bound, and we get the lower bound with Cu equals mu over 2. Now, what was it that we used from the previous chapter? Remember I said we use that orthogonalization step at the end, and that's comes in right here. So if we use that orthogonalization, we have some statement like this or like this, and that's required for me to get this lower bound involving the energy sections. So it's precisely this lower quadratic trap that I'm using along or for that energy section. Remember, the energy section here is gotten because I've decided to go, when I do my orthogonalization step, I've decided to use an energy section to do that. That's actually what orthogonalization means. And so I'm allowed to use the fact that I have the derivative equal to 0 along that energy section, and that allows me to use this inequality. So the precise one that I'm using is this one. Okay, this difference in energies is greater than this difference. And where did I use that? I used it right here. That's it. So that's the lower bound on corrections. Now, to get the upper bound on corrections, it's a whole lot of work and effort and pain and suffering. But I'm going to go through it rather quickly, and I'm going to try to highlight just the important points of the analysis. The tedious stuff is stuff you'll never remember anyway, so I just want you to remember where you can find this analysis if you ever need it. Let's review a couple of notions. So for my bounded energy set, I usually label that B, and that's the sublevel set of E starting at a value that I pick randomly to be my initial guess, U0. So I'm looking for all energies which are in this basin, essentially, this convex set where E is less than E0. And that turns out to be a nice, beautiful convex set because E itself is a convex set. So that's great. Now, we have to introduce a bunch of local energies. So it's not enough for me to know information about the ambient space energy, the E. I need some assumptions on this energy EI. And to get that, what I need to do is start with this bounded energy set B. And so what I'm going to do is, well, first of all, let me say this. So the nice thing about the last theorem is that it implies the energy is always decreasing between iterates. So that means that if I start in some bounded energy set, I always stay in the bounded energy set. So that's, first of all, beautiful. That's nice. That guarantees that each of the UKs are in this nice set. But what's interesting is it doesn't guarantee that the intermediate points, these VIs, VI minus 1, VI, K, VI plus 1, etc., it doesn't prove that all of those guys remain in B. I need some more assumptions. So what I'm going to do is I'm going to take B, the bounded energy set with respect to the ambient space energy, and I'm going to pump it up just a little bit. So I'm going to pump it up. So if I have a set, for convex sets, this is kind of simple. All I'm going to do is I'm going to add a layer onto it, which is an extra layer of length square root of chi. Okay, so that becomes square root of chi right there. That length, that layer. And what is chi? Chi is some complicated number. You don't have to worry about it because we're not going to worry about it too much. All you have to worry about is that B plus is this expanded set. So here's my initial bounded energy set, and all I'm going to do is blow that up a little bit like I'm blowing up a balloon. That's called B plus. Now, now let's talk about assumptions on our subspace energies. Now, each subspace gets an energy associated to it. I can pick this in any way I want. There is a lot of freedom here, it turns out. A ridiculous amount of freedom, actually. So how do we do this? Well, we're not going to say how we do it yet. We'll wait a little bit to do that. However, we do need assumptions about the subspace energies the same way we needed some assumptions about the parent energy, the ambient energy. And these are exactly like the ones on the ambient space energy. We need the energy to be Frechet differentiable on VI. That's the basic one. We need them to be, these subspace energies to be strongly convex. And we're going to use a convexity constant of mu I. Now, chances are this is the same constant as mu of the parent space energy, it turns out. We could choose them like that. So a good rule of thumb is to think about this as being maybe the same size in the same order of magnitude as mu. Okay, so we have this mu for the ambient energy, and think about mu I as being roughly the same as that. Strong convexity. And then finally, we need local Lipschitz continuity of the derivative. So we're going to assume that the derivatives of each of the energies are locally Lipschitz smooth, or I could say EI is locally Lipschitz smooth, and the derivatives are locally Lipschitz continuous. So in the following sense, well, that it's enough to just say that. It's enough to just say that. But what we need is we need to know what is the local Lipschitz constant on a certain energy set. So we can't use B because B is an energy set in the parent space. What we can use is a projection of that. So what we're going to do is take the projection of not B, but we're going to take the projection of that puffed up version of B called B plus. And we're going to call that BI. Okay, BI is the projection of the puffed up bounded energy set. Now, it turns out that puffing that we do of this bounded energy set could be a lot. And that means that the local Lipschitz constant I'm taking for BI could be a lot bigger than L, than my original one. That's not doesn't have to necessarily be the case because I have a lot of freedom in how I choose my local energies. And so I could choose that actually to be close to L if possible. And so I'll try to remember to explain one way or technique of doing this later on. In any case, we have these energies, local energies, and they have to satisfy these standard energy assumptions. Well, the first thing I want to say is, or that we would need to know, is it turns out that this puffed up set B plus and also BI, which is the projection of B plus through the linear projection map QI, are both convex. So actually, that's stated here. So the proof of this is fairly simple, and so I'm going to skip that. Okay, so the main result is B plus and BI, which is the projection through QI of BI plus, are both convex sets. The proof is pretty easy to do, and I'll leave it to you to look at those details. Now, because each one of the energies have this very nice properties that they are strongly convex and locally Lipschitz smooth, then of course they themselves satisfy quadratic energy traps. So for example, over the bounded energy set BI, where we have this Lipschitz constant Li, then we have this quadratic energy, so let me back up. This is not quite the quadratic energy trap yet. This is a statement of the strong convexity and local Lipschitz smoothness on BI. That from there you can get to this construction or this inequality. And if V is such that this is 0, so it's a 0 of the Euler-Lagrange equation, so that means we have a minimizer. So what I'm going to do now is I'm going to take V and I'm going to replace it by UI, and that's going to be the minimizer of EI in VI. If that's the case, then we have the quadratic energy trap relative to the minimizer. So, right, so this holds over this bounded energy set on the local subspace BI. There's our bounded energy set. And notice that it's for the EI energies, and it's satisfied with the strong convexity constant for the local energies, MUI, and the local Lipschitz smoothness constant, Li. This, by the way, just to remind you of a true point, this inequality here will hold for all W in VI, not just W in the bounded energy set. Okay, so there's nothing really to prove here. It's just this is stuff we've proved already. So we're just gonna run through that piece of information. Now, I'm going to get back to this momentarily. Why the tau perturbation? So that's something that you should be keeping in the back of your mind always. And so that I'm gonna come back to this point a little bit later. Why the tau perturbation? Well, it turns out the structure is exactly right to make something vanish. And so, or not necessarily vanish, but it's going to make a term something that we can deal nicely with. All right, so let's suppose that the local energies satisfy E2. This proof is a nice short proof, so we'll go through this one. Suppose that the local energies satisfy E2, and assume that SIK is the search direction computed by the FASD method. So remember, we have a search direction, then we orthogonalize that, and that's the last step in that loop of FASD method. Then it turns out this is a descent direction in the sense that, well, the fact that it's a descent direction means this derivative here is less than this number. This number on this side is all positive numbers, okay? And so that says that this is negative, okay? This derivative is negative. So I'm going to show you why this means, with a very simple picture, why this means that this is a descent direction, okay? Descent direction means if I travel in that direction, I'm going downhill. And by proving that this derivative is negative, it's going to show us that we're going downhill. I'll get to that because a picture shows this better than anything else we could do. Now, by the definition of the tau perturbation, the local problem that we have to solve as part of the FASD method is just this. So all I've done is so there's a local problem that I have to solve involving the tau perturbation. I've inserted the definition of the tau perturbation, moved one of the terms over to the left-hand side, and left one of the other terms over on the right. So the left-hand side now becomes this difference. And this is a key point. Remember, one of the derivatives involving EI was evaluated at the full approximation. There it is right there. And that was in part of the definition of the tau perturbation. I've now moved that over to the left-hand side. And so now I'm looking at this difference here. On the right-hand side, I have that, and that's the same term that appears here. That's the same term that appears here. I want to show that this, in order to prove this result, let's just start with this, and I want to show that that's greater than mu I times the norm squared of the difference SIK. All right, so start with this, and what do we notice? Well, this term here looks like the type of term that would appear in a description of, strong convexity. So that's where we're going to apply. So we have the strong convexity of EI, which says that this number, or this computation is greater than this. So that comes directly from strong convexity of the EI terms. But now on the left, the thing which was on the right-hand side is now on the left-hand side. I've just flip-flopped these two terms. Okay. So that is the thing that I'm bounding below, and this is what's left on the left-hand side. So now I've proven this is greater than that. And the second part, all that involves is multiplying both sides by a minus sign, and that's it. Of course, I change the direction of inequalities and blah, blah, blah. Why is this showing that we are going in a descent direction? Well, let me define a function which is basically embodying the orthogonalization step. So we have an energy. We're starting at our last best guess, and we're looking along a search direction, and we're going to move an amount alpha. But we could move alpha in the positive direction or the negative direction, okay? So this is a one-dimensional function, fik, of alpha. And the plot of that is going to look exactly like this, okay? So basically, looking along the search direction is that way. We're going to go down, 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 reach a minimum, and then we're going to go back up. So when we look along the search direction, what we're looking is to see that the directional derivative is negative, to know that we're going in the right direction. Okay, so this function, if I evaluate it at 0, and I take its derivative, that's precisely this derivative right there. And that tells me immediately that my derivative of that function f is negative. That says that you're going downhill. That's good because that orients me. It tells me that I'm going um, going in the plus in the positive alpha direction to do my searching. Now, the way the problem is expressed is it doesn't matter which direction you go in alpha to get the minimum. This is just helpful to know whenever we do some local estimates of this function. So, right, so the idea is we want to get down to this minimum. We want to get to that minimum. So what we want is we want to find the value of alpha I k, alpha sub I superscript k. That's the thing we want in our orthogonalization step. If somebody would just give that to us for free, then we would be the happiest people on earth because it is a little bit of a computation to get this. So what we want to do is later on, well, not later on, I guess, later on in the book, if you go through the book, you'll see that there are ways of approximating the value of this without actually doing a search in this direction. And so that would be quite nice, but for now, we're going to content ourselves with trying to approximate the size of this thing. All right, so I'm going to state a few lemmas that will describe that function. The first one is basically a restatement of exactly what we've already said. The derivative of f at 0 is that derivative which we've already just calculated, previous step, and we showed that that's a negative, so we're going downhill, no problem. Okay, we're going downhill, down, down, down until we reach the minimum, and the minimum is, of course, the minimum, and so therefore every value between 0 and alpha ik is below the starting value, right? That's just saying all these values down here are below the starting value until you get to the minimum. Of course, it is still true that all these values are also below the minimum, but we really only care about those values there. So that's the first statement, very clear. Second statement is a statement about the strong convexity and local Lipschitz continuity of that local function. We can say a lot about the strong convexity and local Lipschitz continuity, and basically these calculations fall out pretty quickly, and so I'm going to skip those as well. These are one-dimensional analogs of exactly what we've done in higher space dimension. Now we're just working with this function fik, Okay, so these are good to have. They're good because a lot of the follow-on lemmas that we're going to do in the proofs, they use these facts. And since we're skipping those, we won't see where they get used, but they are rather important. All right, now it turns out all I need um, to finish up is a good lower bound on alpha ik involving some parameters that I am familiar with. And it turns out a lower bound on alpha ik is mu I over L. I'm not going to go through this proof. I didn't even print it in the slides. Alpha ik is greater than mu I over L. Why that combination? It turns out that combination is really useful for us, as we'll see momentarily. So basically, I'm saying, so what do we call it? Mu I over L. That's some number, okay? Some positive number. That's all I know about it. And that some number is like right in there, okay? We can put it on the graph. Mu I over L. That is a lower bound for that guy. Big deal, right? Well, it turns out, let's just do a slight manipulation of this that will become useful for us later. I think it is the one that we're going to use later is going to be 1 over alpha ik is less than L over mu I. Just invert that guy. So put that in your back pocket for a moment. Don't worry about this one. Don't need that one. Okay, so we're establishing some lower bound for that guy. That is our minimizing point. Do I need this guy? Don't think this one's an upper bound for that. So if you need an upper bound, and I guess we don't need it because I didn't number it, so we're going to skip that one. So, but there's an upper bound that you could put in your pocket and have. All right, final proof of the final class on the final day is this one. Well, we're going to state a theorem and then a corollary. We're only going to prove the theorem. So what's the proof? Or what's this really involved? So this is an upper bound on corrections. We said, remember, that if we could prove an upper bound on corrections, because we have the lower bound, we just turn the golden key and we have the convergence that we want. You don't really have to do anything else. Just you get convergence for free. Now, the upper bound constant is far more complicated than it was previously. Previously, this was all that appeared, just that part of the constant, and this was not there. Okay, so we have to pay a price, and our upper bound constant is expanded a bit, and it could be a bit large. Okay, because why could it be large? Because these guys could be kind of large. The Li over the mu i's, and the Li's or the L itself could be large. So it's not the best bound in the world, but it still works, and you'll still get a contraction factor which is completely independent of n. The reason why it's independent of n is because you're taking a maximum here. Okay, so that's all that really counts. Now, I can make a choice in the way I choose my energies, my subspace energies, so that this maximum is exactly 1. So that this is 1 plus 1, so 2. So 2L is the constant that I would get here. Roughly, that should be on par with CS constant. So that's not so bad. So I can do that. We don't have time, and I didn't actually print a slide for that to discuss why that's the case, or why that's how you do that precisely. But it is written in the lecture notes of the textbook. All right, let's go through the proof of this. So it turned out, as in SSO, if we could find an upper bound for this object here, then we're basically done. And so what we're going to do is we're going to use the idea from SSO, prove this, try to find an upper bound of a certain sort, and then we'll follow the same steps in the upper bound for SSO, and we're done. Now, in the SSO method, what we do is you add and subtract this term in this guy, and you can pair up one of those guys, and the other one you can just cancel it because it turns out to be 0. Now, in this case, it's no longer going to be 0. So in other words, this part here is no longer 0. We can't just throw it away. Okay, so that is this part. Can't just throw it away. So we're going to have to estimate this guy separately. I1, however, we've done this estimation before. This is exactly the thing that we use the strengthened Cauchy-Schwarz and the stable decomposition to satisfy. So we're going to assume that W is arbitrary, but we have a stable decomposition of that W into WIs. That's the standard approach. You immediately sub in for W, the sum of WIs, okay? And then this step is the same. We add and subtract. Basically, we're adding 0. But now, instead of having one of these two integrals cancel and be identically 0, we can't do that. And so we're stuck with having to estimate both of them. Okay, so the first term, you do exactly like you do or you proceed exactly like you do in the proof of the SSO method. You're going to use the strengthened Cauchy-Schwarz and the stable decomposition, and you precisely get this. Okay, so I'm not going to repeat that. That's exactly like SSO. I'm only going to do what's new here. Right. So what's new is we have to deal with I2. Now, I2 was defined as that sum, and this is no longer 0, but I'm going to add some stuff in here which gives me 0. What gives me 0? Well, I'm going to add in this difference here, tau I and this derivative. So tau I and this derivative are precisely what is involved in the definition of the subspace problem involving tau I. So that's what we're going to insert there. Let me go back and show you that one. So the definition of that is about here, right? So tau I is defined there. That is a functional. You put that functional in here. One of those two, well, I'm just going to take them all and put them all on the same side. So I'm going to take this guy and move it over there. Okay, so notice that this W here is in the subspace VI. So now what I'm going to have is a string of 3 functionals against one of these guys, which is a WI. Okay, so that's 3 terms. It's effectively 0. That's exactly what I'm doing. Let's see here. Those 3 terms are effectively tau minus that correction there, or this term here. So tau is this one, and this minus is right there. Those are all 0 in VI prime, which means that if you evaluate that difference with any WI, then it's 0. Great, because that says that all 3 of those terms are 0. And that is precisely why we choose this form of tau I and this subspace problem, because we get exactly this form out. So that's it right there. That explains why the structure of tau I. Now, well, actually, the next step explains the structure of it. I want to estimate this difference and that difference. Notice that this is the signs are precise here and precisely chosen. Okay, this energy minus that energy. Notice that those are energies on the ambient space, the whole space. And this energy and this energy, it's a difference of energies, okay, on the subspace. So I can estimate both of those using local Lipschitz continuity. So this local Lipschitz continuity is on the subspace EI and for the energy EI, or I should say for energy EI. The one thing I would have to check is I would have to make sure that the subspace, that these all played nice, and that this guy stays inside of the bounded energy set BI. And in fact, you can check that. And that's that. All those details are in the book. So I have to check, remember, to make sure that these guys remain in the BI, the bounded energy set. No problem here. This remains, these guys remain in the bounded energy set. So I have my local Lipschitz smoothness, and I'm going to, right, so in that local Lipschitz smoothness, this pops out with its Hilbert space norm. Now, of course, there's a sum out front, so I have to sum all of these guys. This guy doesn't depend on I, but this one does. Next step is to realize that SI is just equal to epsilon I over K divided by alpha IK, right? Because I said epsilon IK is just alpha IK times the search direction SIK. So all I'm doing here is dividing both sides by that. Now you might say, well, hold on, this could be 0, right? But then I would fire back and say, well, no, we've already proved that this has a lower bound, which is positive. So it's definitely not 0. We can divide by it. This is positive, so it comes outside of the norm when it comes out. Now, remember that 10 was a lower bound for alpha IK involving L and mu I. So that's where we're going to apply that bound. Okay, so bound number 10, this guy right here, but we're going to use it in the inverse form. That's what we're applying at that step. Whoop. This step here. That's going to give us an extra L here, which we're going to spring out of prison, I guess. Bring that L, which doesn't depend on I, out front. And then we're left with this constant, which does depend on I, but we can make it independent of I by just taking the maximum of those guys, right? So take the maximum. 1, of course, is already independent. Just take the maximum of those. That constant comes out front. And now all we have to do is estimate this with what? This is just a Cauchy-Schwarz, a standard pointwise or summational Cauchy-Schwarz inequality to get from this one to that. Finally, we can use the fact that we have a stable subspace decomposition to replace this with CA times W norm. We can leave all that, the rest of that stuff alone. Now we're going to put estimates for 1 and 2 together, and it turns out this is the piece for 1, and the piece for 2 that we just did is all of that. So 1 and 2 added together give us that. The nice thing about both 1 and 2 is they have this common factor in there, common feature, which is that term, and maybe they also have a common CA. Yeah, so CA and that are in common in both of those terms. CA, that, and that. So those all come out front. Or, well, they can be factored out. And the 2 terms which are separately coming from 1 and 2 are this one coming from 1 and this part coming from 2. Right. Okay, so that implies that this, let's take this, move it to the other side into the denominator, and then you see that this just becomes an operator or a quotient involved in the calculation of an operator norm. And so that means that we can bound the operator norm with what's left on the right-hand side. Now we're done, because at this stage, once you get here, you just go back and look at the proof for the SSO method. It's exactly the same steps from that point, in order to get the upper bound that we need, which is this guy here. So from that point on, it's just follow that proof for SSO and we're done. Now, what is nice about this proof is that the upper bound and the lower bound just involved mu, just involved the mu for the energy. The upper bound is where all the work comes in. That's where all the action is happening. And it's still not too bad because it is a little bit worse than the SSO method. SSO was just that bit. And this has a lot more, right? Because it has this bit here. But it's roughly speaking, I can, like I said before, we could choose this so that it's roughly 1. It's not, that's not out of the question. So that would make that 1 plus 1, 2, 2 times L. So the big question is, how much bigger is CS than L? And it turns out not that much bigger. Okay, it's comparable. So this is not that bad. It's really like twice as big as what it would be for the SSO method. And in practice, this converges a lot more rapidly than SSO because it's a lot cheaper, but this constant of convergence isn't that bad. All right, finally, we're all done here. Remember, we have that golden key, which says if you have the lower bound on corrections and then you have the upper bound on corrections, then you get a contraction of the energy, which looks like that, which you can turn into a contraction of the norms. But this one's the easiest one to calculate. I forget exactly what is the formula for calculating this contraction rate rho, but that was part of that little technical lemma, which I'm calling the golden key. So you can go back and look at that. That was just earlier in this chapter. Put the two upper bounds together, the upper bound and the lower bound, and you get a contraction. And that is it. That is the convergence of that. The nice thing again is that this is completely n independent because you're taking a maximum here. There's no dependence on n, the number of subspaces. All that it's dependent upon are these parameters CA, CS, which are, again, also independent of, or should be independent of n, the number of subspaces. This mu and L, which are essentially just describing the structure of the energy. You can't change that. These subspace local Lipschitz constants and constants mu I are, again, in the best scenario, you can choose those so that they're just equal to 1, that ratio is 1. And so those aren't that bad either. But that's it for multigrid. That's it for the nonlinear stuff, and we are done. So we'll stop there and take your questions.